Thank you, and thank you, the organizers, for giving me this opportunity to speak in this great conference. So, my talk is about finite type invariants of knot in homology spheres, and I will directly begin with definitions in order to make clear for everybody, especially what are these three first words in the title. And after giving these definitions, I will give a brief overview of some background of this notion of finite type invariants. So, let's begin with the notion of finite type invariants. So, in our case, we will consider finite type invariants of QSK pairs. So, these are our objects. What I call a QSK pair, MK, is a pair made of a rational homology 3-sphere N, or Q sphere, and a knot K in N, which is null-homologous, meaning that its homology class in the first homology group of M is 0. Okay, so these are our objects, and we will study finite type invariants of these objects with respect to some moves that are called null Lagrangian preserving surgeries. So I won't give a precise definition of this surgery move, just briefly. So that's a surgery move, meaning that we cut a piece of the manifold and glue another one instead. So here the pieces that we replace are rational homology entangled bodies that are embedded in the complement of the knot. And when we make these replacements, we have one condition, which is that the Lagrangian of these bodies is preserved. So essentially, this condition means that this surgery move preserves the homology with rational coefficients. So in particular, here it preserves the fact that we are dealing with Q spheres. And we have also some homological condition with respect to the knot, which implies in particular that the fact that the knot is null-homologous will be also preserved. So we have a surgery move on the set of QSK pairs. So now with this set of objects and this set of moves, we can define the notion of finite type invariants. So for this, we introduce a very formal rational vector space, F0, which is the space generated over Q by all QSK pairs up to orientation preserving homeomorphism. And we consider a filtration of this space. So we define some subspaces Fn for all positive integers n generated by some brackets where each bracket is defined by a QSK pair Mk and the Ci are null Lagrangian preserving surgeries with disjoint supports. So the fact that the surgeries here have disjoint supports implies that we can perform all the surgeries simultaneously. So this allows to define these brackets as the sum over all subset capital I of the set 1 to n of the -1 to the coordinate of capital I times the pair obtained from MK by performing all the surgeries Ci when I is in capital I. So here we have the sum of all QSK pairs that can be obtained by performing some of the surgeries Ci with a sign corresponding to the parity of the number of surgeries. Okay, so this gives a subspace of F0, and it's easy to check that we have a filtration. And now we can, from this, from this we can define the notion of finite type invariance. So an invariant lambda of QSK pairs with values in some rational vector space V is a finite type invariant of degree at most n if its Q-linear extension say lambda bar defined on F0 vanishes on the subspace Fn plus 1. Okay. So this is the notion of finite type invariance. Maybe a way to understand this definition is to consider that when we evaluate this linear extension lambda bar on such an alternating sum, we can think of it as a derivative of the invariant lambda of order n. So what we are asking here is that all the derivative of lambda from the order n plus 1 are vanishing. So we sometimes say that finite type invariants are invariants that have a polynomial behavior with respect to the move that defines the theory. Okay, so now when we are given such a theory, we can consider the graded quotients, the quotients associated with our filtration, and we will look at the associated graded space. Now, it's clear from the definition that the dual of this graded space is the space of finite type invariant graded by the degree. So one of the main goals when studying,
I just had a question about the surgeries.
Yeah.
In the simple case where the handle body would be a solid torus, so are these all possible plane surgeries or with certain slopes? Just to get if it's not probability.
I will not think of it in this term, but I think that's more general anyway. Since we consider here rational homology.
Yeah.
So, in particular, you can insert any kind of a torsion in the manifold.
Okay.
So one of the main goals in the study of such a theory of finite type invariants is to give a combinatorial description of this graded space. Now, the idea to give such a description is to construct some graded space of diagrams associated, adapted to the situation, together with a surjective map onto the graded space G. And in order to prove that this description is complete, one needs to exhibit a universal invariant. The universal in the sense that it induces the inverse of our map, our surjective map. So in particular, this means that this invariant has to induce a map on the graded space. So it means that one has to prove the behavior, to study precisely the behavior of this invariant with respect to the move that defines the theory. Okay, so now what we can see in this definition is that if I take another set of topological objects and any set of moves on these objects, I can give the same definition, and I have an associated theory of finite type invariants. So I like to mention a few important such theories. So the first theory of finite type invariants was introduced by Gusarov and Vasilev, and concerns knots in S3. And the move in this case is the change of crossing. In this case, finite type invariants are also called Vasilev invariants. And the graded space associated with this theory has been combinatorially described by Barnatin and Kontsevich with as a universal invariant the Kontsevich integral. So proving that the Kontsevich integral is universal among all finite type invariants of knots in S3. So then different theories were introduced for three manifolds. The first one was introduced by Otsuki and dealt with integral homology spheres. And there has been many theories proposed for three manifolds. One important one is due to Gusarov and Habiro independently, and can be defined for any kind of three-dimensional manifold. And the move in this case is the so-called Borromean surgery. Okay, I don't detail this surgery move. In this case, the associated graded space has been described in the case specifically of integral homology spheres. So for these spheres, this is due to Gaoufalidis, Gusarov, and Polyak for one part, and for the other part. So they gave the description of the graded space for these spheres using as a universal invariant the LMO invariant of Lemo, Akami, and Otsuki. An interesting thing in this case is that you can use another universal invariant. So there's the KKT invariant of Kontsevich, Kupperberg, and Thurston. And it appears that both these two invariants are universal in this theory. And in particular, it implies that they are equivalent for these spheres, meaning that two these spheres are separated by the LMO invariant if and only if they are separated by the KKT invariant. And it's an important result because it's the only way we have for the moment to compare these two invariants. So now another theory that I'd like to mention is due to Gaoufalidis, Kricker, and Rosensky, and concerns knots in integral homology spheres with as a move the null Borromean surgeries. So the same move as in the Gusaro-Fabiro theory, but once again with some homological condition with respect to the knot. And for this theory, they have given the description of the associated graded space, once again in a restricted case, for knots with a trivial Alexander polynomial. So the description is given again by Garoufalidis, Kricker, and Résumé. And the universal invariant, in this case, they used the Kricker lift of the Kontsevich integral, that I will call Kricker invariant, which is, strictly speaking, due to Kricker and Garoufalidis. And once again, there is here another possible universal invariant, which is the Lescop equivariant invariant. An invariant constructed by means of integrals, equivariant integrals in configuration spaces. So once again, their description of the graded space proves that the Kricker invariant and the Lescop invariant are equivalent for knots in these spheres that have a trivial Alexander polynomial. So now in our setting, the theory we are studying here is in some sense a rational homology version of this one. We look at null-homologous knots in Q spheres, and null Lagrangian preserving surgeries are in some sense the rational homology version of null Borromean surgeries. And in our setting, the candidates to be universal invariants are once again the Kricker invariant and the Lescop invariant. So the goal of this study is technically to give a combinatorial description of the graded space G. And beyond this goal, there is the idea to obtain some explicit universality properties for these two invariants and to deduce from that some equivalence between them. Okay, so now one point in this theory is that the move of null LP surgery is not transitive on the set of QSK pairs. So we will first, for this, have a look at the Blanchard module of these pairs. So we will look at the Blanchard modules because they will give us a characterization of QSK pairs up to null LP surgeries. So we take a QSK pair MK and we look at its exterior X, which is M minus some open tabular neighborhood of K. So quite obviously, this the first homology group of X is isomorphic to Z and generated by a meridian of the knot. And associated with it, we have an infinite cyclic covering X style over X. And we associate with this covering the Alexander module. So the Alexander module of the pair MK, I denote it by A, is the first homology group of X style with Q coefficient viewed as a QTT inverse module. So here the group transformation of the covering is generated by the action of a meridian of the knot, and it induces an action on the homology. So the multiplication by T on this module is given by this action of a meridian of the knot. So we have this module over QTT inverse, and it's known that it is finitely generated, and it's a torsion module over QTT inverse. So in particular, we have a well-defined annihilator that I will usually denote by delta. And now on this module, we define the Blanchard form, which is a Hermitian form with values in Q parenthesis T over QTT inverse, also called the equivariant linking pairing. So I don't write down the complete definition, but the idea is that when we take homology classes in A, we can realize them as knots in X-tiled, and using the group of covering transformations, we define some notion of equivariant linking, and that's what gives us the Blanchard form. Okay, and what we call Blanchard module is the pair AB, the Alexander module equipped with the Blanchard form. So now, the reason why we are interested in this Blanchard module is the following. So given two QSK pairs, they are related by null LP surgeries if and only if their Blanchard modules are isomorphic. So the Blanchard module exactly characterizes the QSK pairs up to null LP surgeries. Here I should mention a similar result used in the Garofalidis-Kricker-Rosonsky theory, which is due to Garofalidis and Rosonsky. They proved the same thing for knots in these spheres with null Borromean surgeries and using the Blanchard module over Z, so defined as a ZTT inverse module. And the result is indeed based on deep results of Matveev, Trotter, and Neck and Stanford. Okay, so once we have this characterization, the idea is that we can fix a Blanchard module AB, and before fixing AB, so the idea is that we have a splitting of our filtration. So we see that the space is Fn split as the direct sum over all possible isomorphism classes of Blanchard modules of some spaces Fn-AB that are defined as previously, but are restricting to QSK pairs that have this Blanchard module. And so the splitting is also valid for the quotients Gn. So now to study our graded space, we fix the Blanchard module AB. And we study the graded space GAB, defined by all the GN AB. And another consequence of the theorem is that for n equals 0, we see easily that G0AB is isomorphic to Q. Once we have fixed the Blanchard module, we have no more degree 0 invariant, except constants. Okay, now to describe the whole graded space GAB, I will introduce some diagram spaces in order to try to obtain this picture there. Okay, so we still have our fixed Blanchard module AB, and we will define a notion of AB colored diagram. So an AB colored diagram is a unit equivalent graph with some labels. So there are quite a lot of labels, so I will give them on an example. So we draw a unit equivalent graph. So for instance, think like this. And on this graph, I will put some labels. So first, the trivalent vertices are oriented in the sense that we fix a cyclic order of the 3 half edges that meet at this vertex. Then the edges are oriented and labeled by some polynomials in QTT inverse. Okay, then the univalent vertices are also labeled. They are labeled by elements of the Alexander module A. And the last thing, for each pair of univalent vertices, we fix rational fraction Ft. So for each pair, so we have also one here, and one here. Okay, and we have a condition on this rational fraction. So here, these two univalent vertices are labeled by eta and nu, and the condition is that the Blanchard form applied at the couple eta nu must be equal to this fixed rational fraction up to polynomial. Okay, so these are our AB colored diagrams, and indeed we add one more thing. We will indeed consider augmented AB colored diagram, meaning that we add some isolated vertices so for instance, here I add 3 isolated vertices, and they are also labeled. They are labeled by prime integrals. Okay, so these are our diagrams, and from this definition, we can define our diagram space. So we define the space AN og of AB as the rational vector space generated by all augmented AB colored diagrams of degree n. So here the degree is the number of 0 or 3 valent vertices. And we quotient out by a family of relations. So sorry, I don't give the relations because it would be too much. So anyway, we have this diagram space, and it appears to be at least a good candidate to describe our graded space G. So the result is the following. There is a canonical surjective Q-linear map phi n from A and og AB to Gn AB. Okay, so of course we'd like to have here an isomorphism, but I can state it only in some specific cases. So if the Blanchard module is trivial, then phi n is an isomorphism for all n. And the second thing, if the module AB, the Blanchard module, is the direct sum of capital L isomorphic Blanchard modules, and I will go on the next blackboard. So if we have a direct sum of capital N isomorphic Blanchard modules, then phi n is an isomorphism if n is at most 2/3 of capital N. Okay, so we have these cases where we have an isomorphism. So a few words maybe on this result. So I will roughly give a description of the map phi n in order to make sense to the relation between diagrams and graded spaces associated with finite type invariants. So maybe a fast historical remark. So such diagram spaces have been yet used to describe graded spaces associated with finite type invariants. So in particular, for the description here in the Gusarov-Habibo theory. So there, for these spheres, they used trivalent diagrams. So it's only trivalent vertices with orientation and no orientation or labels on the edges. So this was the diagrams used in the Gusarov-Habibo theory. And Gabrofalidis, Kricker, and Wronski, Gabrofalidis and Wronski introduced the idea to put orientation and polynomial labels on the edges in order to describe the graded space associated with knots in this sphere with a null Blanchfield module, trivial Blanchfield module. So here we add some univalent and isolated vertices. The isolated vertices here are there indeed to consider the cardinality of the first homology group. So you see that in the case where n equals 1, we have these univalent vertices that appear, and because of the relation I didn't give, we have in degree 1 only these isolated vertices. And a vertex labeled by some prime integer p via the map phi n, so phi 1, and passing to the dual, corresponds to a degree 1 invariant, which is the p-adic valuation of the cardinality of the first homology group. So of course, these do not appear when you treat these spheres, since the first homology group is trivial. And the univalent vertices here appear in order to deal with the case of a non-trivial Blanchfield module. So we will see how it works by giving a rough description of the map phi n. So maybe begin there. So map phi n. So we have our fixed Blanchfield module, and we also fix a QSK pair with this Blanchfield module, and we take an augmented AB colored diagram, say D. And first, we embed D into a ball in the complement of the knot in M. And then this embedded diagram, we will modify it. I erase here. We will modify this embedded diagram in order to obtain some surgery data. So first, if we have an edge with some label t to the k, we will modify this edge in the following way. We have somewhere in our manifold the knot k, and we take a piece of the edge and make it turn around the knot k. K times. So that's the meaning of this power here. And thanks to these relations that I did not give, the fact is that diagrams with powers of t on the edges generate the whole diagram space. So we only need to look at this case. So then, when we have an edge between two trivalent vertices, we insert in this edge a little uplink in this way. Okay, and now for the univariant vertices, if we have a univariant vertex labeled by some gamma in the Alexander module, you glue at this vertex a simple closed curve, say L, such that when you lift L as some L tile in the infinite cyclic covering, its homology class is equal to gamma, so the label of the univariant vertex. And then if you have a second vertex with some label, for instance, eta, so you also glue a loop there, such that a lift has the homology class eta. And remember that we also have here between these two univariant vertices, we have a fixed rational fraction. And we ask that, so the equivariant linking of these two lifts is exactly this fixed rational fraction. So this equivariant linking, that was the equivariant linking defined in the infinite cyclic covering, sorry, there is tile here, and which is used to define the Blanchard module. So up to polynomial, this is the value of the Blanchard module applied to gamma and eta. Okay, so once we have made all these modifications on the diagram, what we get is from the diagram D, we have a disjoint union of graphs of this form that are called Y graphs, and we have still our univariant vertices, isolated vertices. Okay, so now the idea is to associate to each connected component a surgery. So So for the first case, when we have a Y graph, we consider a tabular neighborhood of it, which is a genus 3 underbody. And we associate with it a 6-component link inside this tabular neighborhood. And what is called the Borromean surgery along the right graph is the usual surgery along this 6-component link. So this is the so-called Borromean surgery, which appears in the Gusarov-Fabiro theory of finite type invariants. And the fact is that it's a specific case of Lagrangian preserving surgery, and that from the construction we have that it also satisfies the nullity condition. So we have a null LP surgery here. And last thing, when we have an isolated point labeled by some prime integer p, we associate with it a surgery which is replace a little ball B3, for instance a neighborhood of the point, by a rational homology ball, say BP, whose first homology group as order P. So this, of course, is associated with the degree 1 invariant that I mentioned, that has a periodic valuation of the cardinality of the first homology group. Okay, so what we get now is that from a diagram, an augmented AB colored diagram of degree n, so degree n means that we have n 0 or 3 valent vertices. So we obtain here n connected components, Y graphs or points, and so we get n surgeries in our manifold. So this defines a bracket in the quotient GNAB. So this makes sense. We have such a map. So of course, there are many choices in the definition. So we have to check invariance. We have to check that it satisfies the relations defining the diagram space. And we have to check surjectivity. So this gives this canonical map. And of course, once we have this surjective map, we want to know if it is an isomorphism or not. So we have seen in the theorem that there are two cases where we have isomorphism. So to finish, I'd like to explain how we treat the question to know whether phi n is injective or not. And for this, we use potential universal invariants. So here, we will consider the Kricker invariant and the Lescop invariant. So, okay. So finally, we consider universal invariants. So as I said, we have two candidates here to be universal invariants that are the Kricker invariant that I will denote Z3 and the Lescop invariant ZS. So indeed, these two invariants will have the same role in our setting, and the properties that I will give are the same for both invariants. So I will just consider an invariant Z, which is either the Kricker invariant or the Lescop invariant. And another thing is that from this invariant Z, we can construct another invariant, more complete invariant, by adding the datum of the first homology group of the manifold. So this gives an invariant that I call Z-aug, augmented. And so the first thing that I will tell here is what is the space of values of this invariant. So for this, I have to introduce other diagrams that are related to the previous ones. So once again, we fix a Blanchard module AB, and we denote its annihilator by delta. And we have a notion of augmented delta colored diagram. So such a diagram is a trivalent graph. So we have no univalent vertices here. So once again with some labels. And once again with isolated vertices. So I will give the label on an example. So we can take a simple equivalent graph, the theta graph. So we still have the orientation of the equivalent vertices and the orientation of the edges. But now the edges are labeled by rational fractions living in 1 over delta t qtt inverse. So here we have three such rational fractions, and we still have the isolated vertices labeled by some prime integers. Okay. So we can define from this the space AN of delta as the rational vector space generated by augmented delta colored diagrams of degree n. So our degree is once again the number of 0 and equivalent vertices. So here that's all the vertices. And once again we quotient by some relations. Okay, so now we can give some important properties of the invariants of Kricker and Lescop. So we have a theorem. So the invariant Z org is a family of invariants, the n org for non-negative integers n, where the n org takes values in a n org delta, and the n org is a finite type invariant of degree n. That's the important part for us. So this is due to Lescop for her invariant, and myself for the Kricker invariant. So the finiteness properties for the Kricker invariant were proved previously for in restriction to null Borromean surgeries by Garofalidis and Kricker. So with this result, we see now that these invariants fit into our theory, and we can use them to try to prove that phi n is an isomorphism. So the point, the picture is this: we have the space AN org of AB. We have our surjective map phi n to the quotient GNAB. And since we have these finiteness properties, Zn org induces a map on this quotient with values in AN org of delta. Of course, the problem here is that we don't have the same diagram space here and here. So we don't obtain directly the inverse of phi n. So the idea is to consider the composed map here, tidied out by psi n, and to ask whether this map is injective or not. So the map psi n is quite easily described. So the map between the two diagram spaces. The idea is that when you have your diagrams with univalent vertices, you can glue two univalent vertices to create an edge. And the label of the edge will come from this fixed rational fraction between the univalent vertices. Then you have a sum over all possibilities to glue univalent vertices together, and this defines the map psi n. Anyway, the description is simple, but the study of the map is not so easy. So we have the question, is psi n injective? If the answer is yes, so phi n is an isomorphism, and we are happy. So the answer is yes when the Blanchard module is trivial. In this case, indeed, since the labels of univalent vertices are always zeros, we easily see that we have the same diagram spaces, and psi n is the identity. So we have also the other condition that appears in the theorem, so I don't rewrite the condition. But so when the Blanchard module is the direct sum of n of isomorphic copies, then psi n is injective. Indeed, the fact that we have n of isomorphic copies allows to define concretely the inverse of the map psi n. So here we have isomorphisms everywhere on this diagram, and so things work. Anyway, in general, it's not possible to define the inverse of psi n. So with Benjamin Audoux, we studied, in particular, the case n equals 2. And we have some results in this case for little Blanchard modules. So the result is the following. So first, if the Alexander module A has Q dimension 2, then psi 2 is injective. And here we can have add but not surjective. So that we don't, so in this case, psi 2 is injective, so phi 2 is an isomorphism. But we see that since it's not surjective, Z2 does not induce in this case an isomorphism with the other diagram space. And the last case, if the Blanchard module AB is the direct sum of two copies of the same Blanchard module, where A0 has Q dimension 2 and order or annihilator delta, then psi 2 is injective if and only if the order delta is different from t plus 1 plus t inverse up to an invertible. Okay, so this is the result we got for psi 2. And of course, the most important point in this theorem is that we have a counterexample to the injectivity of psi 2. So when we have the direct sum of two Blanchard modules isomorphic and with order t plus 1 plus t inverse, then psi 2 is not injective. So in this case, the alternative is the following. Either the map phi 2 itself is not injective, and in this case, we have to refine the diagram space. We have to find more relations that are satisfied and that allow to define a quotient of this diagram space on which phi n will induce an isomorphism. Or the other possibility is that phi 2 is indeed an isomorphism. And in this case, it means that we miss some invariant to add to the OG to obtain a complete universal invariant, which is universal for finite type invariants in this setting. So just to conclude, I like to recall that the consequences of such results is that when we know that phi n is an isomorphism, so in the cases that are written here, we know that for the corresponding knots, the Kricker invariant and the Lescop invariant are universal as finite type invariant, and so they are equivalent, meaning that in this setting, they separate the same QSK pairs. Okay, so I stop here, and thank you for your attention.
Thank you very much. Question or comment, please? So in case non-injective, do you know explicitly the element in the kernel?
Yeah, we have a generator of the kernel. So we have generators of the kernel of psi 2. So as a linear combination of 4 diagrams. And we also have realized it as an element, so it's image by phi 2. So we have some surgery representations of QSK pairs that give the image of this kernel.
And what is the difficulty in computing phi 2 on this guy?
The difficulty is not really to compute phi 2 on this guy. It's now the problem is to understand this element in the quotient G2. Is it trivial or not? So either finding the invariant, which will prove that it is not trivial, or finding some topological relations to prove that it vanishes in the quotient.